Hello everyone. So this is lecture 2 for assembly language programming. I don't know what happened with lecture 1. It wasn't that clear, so regarding the question I asked in it, you can leave me a comment. Don't worry about it. I already know. I might redo it. I'll check it. I'll see what went wrong, and we'll go from there. But this is lecture 2, and here's what we're gonna cover today. Some important concepts and how to represent data representations. We know we have different data we mean to the machine. We have video, audio, graphics, integers, floating points, all those. We're gonna see those. We're gonna concentrate on integers, signed integers, characters, hexadecimal, octal, mainly those. I don't think we're gonna go into any of the others in detail, but this is what I'm trying to do in the first lectures. We're trying to know the hardware. Remember, assembly language is a low level. It's near the hardware. We need to know some details about the hardware. And last one we took, for example, the memory hierarchy. That's really important to know what's a register. A register is a memory location. And we're going to take here a binary numbering system, the 0, 1, or the machine language, converting binary to decimal, and converting decimal to binary. Decimal is our numbering system, the 10, 9, 8, 7, and how to convert from binary to decimal and from decimal to binary, from our numbering system to the machine numbering system, and from the machine numbering system to our numbering systems. And those concepts, remember guys, are really important. Compilers, remember we said compilers translate the whole code and is faster. Interpreters, statement by statement. And if you remember in the lecture 1, I said Java and C and C++ has some differences. One of the differences is Java consider an interpreter where it takes one instruction, translates it, compile, generate the bytecode, run it, and then does that to the second instruction, third instruction. In C++, what it does, it takes the whole instruction at once, translates them, and then run them. This is the difference between compilers and interpreters, but both of them do the translation part. Compilers are considered to be faster. Transistors, and this is really important. What's a transistor? A transistor is a switch. What do I mean by a switch? An on off. If the switch is open, it means it's off. It's 0. It has a value of 0. If the switch is closed, it's on, having a value of 1, passing the current. Think of the switch for the light, on and off. And why this is every electronic device is the base building block of it is transistors, which are, think of them as zeros and ones. From a transistor we can build gates, and we're gonna go gates in lecture 8. We're gonna explain it in more detail. We have mainly 6 gates: the AND, OR, NOR, XOR, NAND, NOT. I'm not sure if I forgot one of those. Are gates. From transistors we can make gates. From gates we can make what? Integrated circuits. What is an integrated circuit? An integrated circuit is, for example, a CPU is an integrated circuit. A chip that does. A graphic card is an integrated circuit. A GPU is an integrated circuit. An FPGA is an integrated circuit. All those are considered integrated collections of gates that does a specific task. But remember, transistors are the base building block for any electrical device. From transistors, what can I get? I can get gates. We have mainly 6 gates. From gates, what can I get? An integrated circuit, for example, a CPU. Now, this is a really important principle of equivalent of hardware and software. What does that mean? Anything I can do in hardware, I can do as a software, and anything I can do as a software, I can do as a hardware. And try to think of it. The programs, what we took in lecture 1, any program is translated to what? Machine language, 0 and 1. 0 and 1. And what did I say a minute ago about the base building block for any device? It's a transistor. A transistor is what? A 0 and 1. So think of a program translated using a compiler to a 0-1 machine language if you want to implement it as a hardware, as transistors, which are zeros and ones. Go get the zeros one in machine language and implement it using the transistors zeros ones. That's considered a hardware. So now what's the difference between them? Why do we go hardware? Why do we go software? For example, a CPU is an integrated circuit. It's done as a hardware. Can we do it as a software? Yes, you can. We can do. But the problem is a CPU needs to be fast. Hardware is much faster than software. So we do it in a hardware. Programs that are, and this is what we get from software, is flexibility. Programs that we need to change frequently, we need to write them in software. They're slower, but what do we gain? Flexibility. We can change them in one night. Hardware, no, there's a whole big process that goes into it. It can take up from 12 to 18 months to generate the hardware. 12 to 18 months. This is the principle of equivalent. Remember, if I need speed, we go what? Hardware. For example, graphic cards, CPU. What else? Hardware. Don't think monitor and those. For example, in cell phones, they have a let's say encryption algorithm, or they have an error detection and correction mechanism. And in communication, we need speed. So that algorithm, the error detection and correction, is going to be implemented as a hardware to gain speed. On a cell phone or a smartphone, we need what? Speed, especially in communication. We can implement it as a software, it's an algorithm, but we go hardware because we need the speed. Remember, software gives us flexibility. Instruction set architecture. And think of this is really important. ISA. Think of them as think of it as the vocab that the machine recognizes. Remember, we took in lecture 1 move, add, mul. Those are what? Commands or instructions that a machine can understand. And every different architectures or different machines family understand different instructions. That's why we have different assembly languages. So we call those set of instructions as an instruction set architecture, ISA. The vocab or the instructions that a machine understands. Now let's go to the binary numbering system. We have digits. Digits are called bits. So, for example, this is a bit. Let's turn on the pen. This is a bit. A digit. This is a bit. Bits. 0 and 1. The smallest part. But it can't be memory like 1 bit. The smallest allowable memory is a byte. A byte is 8 bits. Here we have a byte, 8 bits. And usually in computer we start with 0. This is bit 0, this is bit 1, this is bit 2, has a 1 in it, this has a 0, 0, this is bit 3, this is bit 7, has a 1 in it. A bit can only have a binary. Binary is 1 or 0, true or false, on or off. This is what's a binary number system. That's why they call it base 2. Base 2, it only has two values, 0 and 1. 8-bit, this is an 8-bit. All of this is called what? A byte. 8-bit equals a byte. And it's gonna appear there. 8-bit is 1 byte. So 16-bit is 2 bytes. 3 bytes is 24 bits. And here, the most significant bit, the bit that has the highest value, and it's the last bit on the left side. That's the bit that has the most significant value. They call it the most significant bit. The most significant bit. The least significant bit is the one with the lowest value, the one on the right. And we're gonna need to know this, the most significant bit and the least significant bit. We can say also the most significant byte and the least significant byte if we had a collection of bytes. But think of it, most significant bit, the bit with the most significant value, and we'll see why is it the most significant value. Binary, base 2. Base 2 meaning it takes two values, 1 and 0. This is base 2. Those only what? Don't look at those. Those I'm just numbering, and I'm numbering the bits. Those are the values. They can only take 0 and 1. What does that mean? I can't have a value 2 here. That's not a binary value. A 2 is not a binary value. It's base 2 only has two values. Base 2 has two values, 0 and 1. Now, how many things can we represent using m bits? This in one bit. If I have 1 bit, a 1 bit can either be 0 or 1. I can represent two things in 1 bit, 0 or 1. That's two values, that's two things, and we can say 2 to the power what? 1. That's 1 bit. Now in 2 bits, how many things can I represent? 2 bits, I have one value can be 0 0, I can have 0 1, I can have 1 0, I can have 1 1. Those are the only possible values using 2 bits. So I have 4 values, so I can represent 4 things. So think of it as 2 to the power 2. This is the number of bits. Why did I use 2? This is the base 2. 3 bits, how many things can I represent from the equation? I'm using base 2 and I have 3 bits, so I can represent 2 to the power 3 values, which is 8, which is actually from 0 to 7. Here from what? This is value 0, this is 1, this is 2, and this is 3. From 0 to 3, 4 values. Here from 0 to 7, 8 values. 4 bits, how many things can I represent? Here are all the possible values I can represent in 3 bits. In 4 bits I can represent 2 to the power 4, which is 16. In 5 bits, 2 to the power 5, 32 bits. And 32 things, I mean, from 0 to 31. 16 from 0 to 15. In 6 bits I can represent 2 to the power 6, which is 64 things. So I can represent from 0 to 63. And why do I say how things I can represent? Meaning I can say 0 represents what? Black. 1 represents white. 0 represents on, 1 represents off. That's a 0. We can program it as we want. We can say colors, a traffic light, red and green only. Red and green, true or false. So this is the number of bits, and 2 is the base. 2 is the base. 2 to the power 8, meaning 1 byte. In 8 bits is 1 byte. 1 byte, I can represent 256 things which have the value from 0 to 255. 0 to 255. It's always 1 less because we took the 0. And in bits, this is what we want. I can represent 2 to the power n. 2 to the power n things. Or now binary numbering, we have what's called the positional notation. And what do I mean by positional notation? Let's say I have 920 in our numbering system, which is base 10. According to the positional notation, this 0 equals what? 0 multiplied by what? 10 to the power 0, which gives me 0. This 2, what does it represent? 2 multiplied by 10 to the power 1. Its position. This is position 0, position 1, position 2. 10 to the power 1 is what? 10. Multiplied by 2 is 20. So I'm saying 0 plus 20. The 9, what does it represent? Let's put plus. 9 is 9. What's its position? It's 2. So multiplied by 10 to the power 2. 10 to the power 2 is 100. Multiplied by 9, 900. So this is the positional notation. I can break my 920 to 900 plus 20 plus 0, which is 920. Now let's see how I do it. Base 10 is the regular numbers we know, which 0 to 9. Base 10, 0 to 9. Don't think 10 is a number. 10 is 2 digits. So the only possible digits that I can have in a base 10 numbering system is from 0 to 9. I can have 99, 98, but that's 2 digits. But 9 and 8 is variable digits. 10 is 2 digits, which is 1 and 0. 35 is what? 2 digits, a 5 and 3, and both of them are valid because I can have digits from 0 to 9 in decimal. In what? Decimal or base 10. I can have here 2691. How can I represent this using position notation? The 1 equals what? As position 0. This is 1, this is 2, this is 3. So the 1 equals what? 10 to the power 0. Why did I use 10? Because I'm using base 10. Base 10. So 1 multiplied by 10 to the power 0 is what? 10 to the power 0 is 1. 1 multiplied by 1 is 1. Plus what? 9. Now 9 is in position 1. So I'll have 10 to the power 1 multiplied by 9. 10 to the power 1 is 10. Multiplied by 9 is 90. So I'm saying 1 plus 90 plus what? I'm going to have 6. What's the position of 6? It's 2. This is 0, 1, 2. So I'll have 10 to the power 2 multiplied by 6. 10 to the power 2 multiplied by 6 equals 600. So I'll have 600, 9, and 1 plus what now? I'm going to have 10 to the power 3 position of this number multiplied by the number equals 2000. If I add all of those, that will give me that number. And this is easy to notice here because it's decimal is tens, multiple of tens. So we can break it from here to a 1, 90, 600, 2000. You can know from that. But now how do I do that in binary base 2? Each bit power of 2. Why base 2? We said 10 base 10 or decimal is power 10. So here power of 2. For example, I have bit 0 is 2 to the power 0. Bit 0 is 2 to the power 0, having a value of 1. Depending on that bit, do I have a 0 or 1? I multiply it by this one. If I had a 0, I'm going to have what? 1 multiplied by 0, it's what? 0. If I had a 1, 1 multiplied by 1 is 1. Those are the only two values. Now, if 0, this is what's going to happen. 2 to the power 0 multiplied by 0. If 1, okay, this is, we took it in two different, 2 to the power 0 equals 1 multiplied by 0. So here's what I'm doing. This is 2 to the power 0 equals 1 and 0, which equals 0. If bit equals 0, 0. If bit equals 1, bit 0. If I have, meaning bit 0 here, if I have 1 bit and it has a value of 1, how can I represent it? I want 2 to the power 0, which is the bit 0, multiplied by 1. 2 to the power 0 is 1. 1 multiplied by 1, it will give me what? A 1. A 1. If 1 equals 1. And here it is. Now base 2, each bit 1. And this is what I mean by bit 1. This is my bit 0, first bit. Now this second bit, which is bit 1, and this, don't think this is the values. Here I'll have bit 2, and here let's say I'll have bit 3. What's the value of each bit? So this is 1, so I'm gonna have what? 2 to the power 1 multiplied by whatever I have in that bit. If I have a 0, it's gonna be 0. If I have a 1, it's gonna have what? 2 to the power 1 is 2, multiplied by 1 is gonna give me a 2. So now, if it's 0, if bit 1 is 0, I'll have what? 2 to the power 1. Why? Bit 1 multiplied by 0, which is 0. If I had it 1, I'm saying what? 2 to the power 1 multiplied by 1. And why did I put it this? We're gonna see, let's see, this one equals 2. Example, 5 bits. Now bit 0. So what's the value of this? It's gonna have the value of 2 to the power 0 multiplied by whatever I have in it. This is gonna have 2 to the power 1 multiply, oh 1, sorry, multiplied by what I have in it. I'm not sure, should I go back and change whatever? Now bit 2, what? 2 to the power 2. 2 to the power 2 multiplied by whatever I have. Is it 0 and 1? This is 2 to the power 3. And this is 2 to the power 4, and I multiply it by whatever I have in. So here's what I got: 2 to the power 0, 2 to the power 1. This is the value of each bit. So this is the bit with the most significant value. Most 2 to the power 4. This is the bit with the least significant value, 2 to the power 0. So think of this as what? 2 to the power 0, 1. 2 to the power 1 is what? 2. 2 to the power 2 is 4. 2 to the power 3 is 8. And 2 to the power 4 is 16. 2 to the power 5 is what? 32. 2 to the power 6 is what? 64. We double. We keep doubling. So now example, I have those 5 bits. 5 bits. What I can say is I have 1 multiplied by 2 to the power 0. I got this one. And now 0 multiplied by 2 to the power 1. So this is going to have a value of 0. This is going to have a value of what? 1. And this 1 multiplied by 2 to the power 2. 2 to the power 2 is 4. So now I'll have 4 here. I have 1, 0, and 4. And this is going to be 0 because I'm going to have 0 multiplied by 2 to the power 3. I don't care what 2 to the power 3 equals because I have 0 is going to be a 0. This one is going to equal what? 1 multiplied by 2 to the power 4, which is 16. So this number in decimal equals what? 16 plus 4 is 20 plus 1 is 21. Is how we did it. We broke it, this, and we now multiply it. So 1 to the power 0, this is representing the value of this, which is what? 2. Now this one, 0 to the power 1, 2 to the power 1 multiplied by 0 gives us what? A 0, whatever we have. Now the third bit, I'm saying 1 multiplied by 2 to the power 2 is this, is going to equal 4. And here, sorry guys, here I should have a 1, not a 2. Not a 2 to the power 0. And 0 to the power 3 is going to be what? 0, I don't know why I had that missing. 1, and this is going to have a 16, or this is right, 2 to the power 4. Oh, I didn't come to, sorry guys. 2 to the power 3, this equals 0, and this equals 16. And this should be 1. This is my only error. This is how to convert from what? Binary to decimal. Now let's say we have this is 5 bits. This is what I do. Instead of using 2 to the power 0, I start with 1, 2, 4, and keep doubling each bit. 8, ooh, 8 and 16. So now wherever I have ones, I'll add those. So I'll have 21, which is here are those, this one, and this one. So this is a 1, 0, 4, 0, 16, which is 21. And this is, I'm just breaking it down how I got the value 1. To the power 0 multiplied by 1 to the power 2, depending on the position. This is in position 2 to the power 2. So I start 0, 1, 2, 3, 4. It's 21. Convert the following from binary to decimal. Well, let's put it here. 1, 1, 0, 0. I have 4 bits. This is, I can say 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. But I want to use what? The 1, 2, 4, 8. I double. Start with 1 and keep doubling. You stay on the safe side. So I only have ones here. So I only take those and add them up. So 8 plus 4 equals 12. Let's see, 1, 1, 1. And I have all those 2 to the power 3, to the power 2. Those are going to be zeros. I'm going to have 8 and 4. And we add them up, it's 12. It will be what? Our decimal number. And this is what, when we put them between brackets and I say 10, that means decimal. When I put them between brackets and I say 2, that means binary. Base 2, base 10, base 10. So what's this? Converting the following from binary to decimal. What happened in this one? Same thing. Okay, example, convert the following from binary to decimal. Look how big this number is, but we can break it down to what? Start with 1, 2, 4, 8, 16, 32, and because I have a 0, I have 64, but I'm not going to use it. 128, I'm not going to write it. And here I'll have 256. So my total is 256 plus 32, which is 288, plus 16, meaning 314, plus 8, 322, plus 2. I don't take the 4 and I don't take the 1 because they're zeros. 2 is, and how much did I get to? 314, 322, 324 should be. And here's how it goes. I write them 0, 1. This is 1, 2, 4, 8, 16, 32, 64. I should have wrote numbers. 128. I have a problem with the eighths. And 256. I'm gonna use the pen for mine. So I'm not gonna add this, not this one, because they have values of zeros. I'm gonna add the 256 plus 32, which is 288, plus 16, which is plus 16. 288 plus 16 is 304, and 8, 3012, and 2, 314. Is it 314? 314 should be 314 here. Check it and see the right answer. This is converting from what? Binary to decimal. That's an easy way. Just start with 1, 2, and what do I mean by 1, 2? It's representing to the power 0, to the power 1. This is what? 1. This is 2. This is 4. This is 8 to the power 3. This is to the power 4 is 16. To the power 5 is 32. That's why it's easy to find them. To the power 6 is 64. To the power 7 is 128. To the power 8 is what? 256. And we keep going. That's hilarious. He's giving a joke in binary. Now, how can we convert from decimal to binary? Divide by base, meaning I divide by the base. When I'm using decimal, I divide by base, and I want base 2, I divide by 2. Divide by the base you want and take the remainder. And honestly, we don't need the dividend. If you know the remainder, the mod operator, it's like dividend. It only takes what? The remainder, and that's what we need. And let's say I have 49. What does it equal? I divide by 2 or mod 2. 49 divided by 2 is what? Is 24, yeah? Remainder is what? 1. Now I divide also by 2, or I find mod 2. 24 mod 2 is divided by 2 is 12, and mod 2 equals 0. The remainder is 0. Now again, mod 2 or divided by 2 is 6, and the mod operation is 0. Now 6 divided by 2 is 3, and 3 mod 2 is what? 1. What happened here? 49. I'm saying 6 divided by 2 is 3. And there's no remainder, 0. Now I'll say, okay, now I'll say 3 divided by 2 is 1, and remainder is 1. Here 1. And I think that finished. 1, 1. And if we look at it, now if I took, this is my final answer, 1, 1, 0, 0, 0, 1. And we read, it's important to read bottom up. If I read it this way, from the above, 1, 0, 0, 0, it's going to totally have a different values. But let's check the values. What is this really? 49. I have 1, 2, 4, 8, and I don't reuse them, so this is going to be 16, and this is going to be what? 32. So 16 plus 32 is 48, plus 1 is 49, and that's good. Now example, convert the following from binary to decimal, or should be from decimal to binary. So what do? I do the division operation, or here's what I'll do. I'll do 1, 2, 4, 8. I'll post all the 16, 32, 32, 64, 128. Sorry about the handwriting, guys. And 256. And what do I have? I wrote all those needed to 512. Keep doubling, just keep doubling. I know my handwriting is bad. 512, 256, 64, 32, 16, 8, 4, and 2. So can I take the 512? Yes, 512 is included in the 570. So now I have 1 for the 512. That means he's coming. If I do, now I have to do 570 plus 512, or minus 570 minus 512 equals what? It should equal 58. So I'm left with 58. Is it covered in 256? No, 0. Is it covered in 128? No, 0. Is it covered in 64? No, 0. Do I have a 32 in 58? Yes, I have a 32. So now 58 minus 32 equals 26. 26. Do I have a 16 and a 26? Yeah. I'm left with 10. Do I have an 8? Yeah, I'm left with 2. So I don't need the 4. So here I don't need the 4. It's going to be 0, and here I'm going to have 1. So this is the number. Remember, 1,111 and 01. 1,111 and 01. Let's see if we do it the long division way. 570 divided by 2 is gonna be what? 285. Remainder is 0. 285 divided by 2, it's gonna be 140, 142, and the remainder is 1. 142 and remainder is 1. Now divide the 142 also by 2. It's gonna give me 71 and the remainder is 0. Now divide the 71, it's gonna be 35 and remainder is 1. And now divide the 35 by 2, it's 17 and remainder is also 1. Now 17 divided by 2 is 8 and remainder is also 1. And 8 divided by 2 is 4 and remainder is 0. And 4 divided by 2 is 2 and remainder is 0. And 2 divided by 2 is 1 and remainder is 0. Then I have the 1 and I had over here, what did I have? So is this the right answer? Let's check. Here I have 1 2. Was that a different answer or what? 1 2 4. I don't need the 4, sorry. 1 2 4. Now this is 8, this one is an 8. So let's put, I have a 1 and 2. I have a 2 plus, so I have it more clear here, 8 and plus 16 plus 32. Oh, it took it. 32 was here, plus 0 plus 0, 32, 64, 128, 256. 256. So this gave me a wrong answer. Did I use 570 in the previous example? It gave me 1,111.01. And what am I trying to read? Really important to read what? Bottom up. So did we do an error here? So this is the last one I think we got. 17 divided by 2 is 8 and remainder is 1. 16. 8 divided by 2 is 4, remainder is 0. 4 divided by 2 is 2 and remainder is 0. 2 divided by 2 is what? 1 and remainder is 0. So now it worked. Okay, we had a missing 0 here and here 1, and now I have 1. So my number will be 1 0 0 0. That makes sense. So here I'm missing a 0, guys. Here I'm missing a 0 in the slides. Check it, the division operation. This finishes lecture 2. Hope it was fast and fun. I'm gonna try to make most of the lectures like this, easy, brief. You can check them every day, do some exercises on them. So now what I'll do is I'll go grab, if I was you, I'll go grab a couple of binary numbers, convert them to decimal, a couple of decimal numbers, convert them to binary. There's so much binary to decimal converters, online calculators. Use them just to check your answer is right. Thank you, guys. If you have any questions, please post it in the comment section. If you like, please like the video and subscribe. Please tell the other students about this, my students. If you're one of my students, tell the others, anybody you know, about this. Maybe they're not subscribed, but this is important for the assembly class next semester. Thank you, guys.